Hello friends, this is a project for my wireless communication subject and my name is Stanley Matthew. The topic for the project is orthogonal frequency division multiplexing. First, I would like to go through the outline, so how we are going to approach this project. The first is introduction to OFDM, which is orthogonal frequency division multiplexing. So here we'll come to know what exactly is OFDM. The second is the channel estimation techniques, the different techniques that are used to estimate the channel so that the data is received better. The one of the critical parameters to be considered when using OFDM is peak to average power ratio, and since it is one of the critical parameters, we have to also consider the various ways to reduce it. The next is the error correcting codes that will be discussed, and finally one of the important applications of OFDM when it is combined with MIMO technology. So first, let's go through what exactly do you mean by orthogonal frequency division multiplexing. It is basically a method of digital modulation in which a signal is split into several narrowband channels at different frequencies. In other words, it is a technique, method, or scheme for digital multicarrier modulation using many closely spaced subcarriers. That is, a previously modulated signal modulated into another signal of higher frequency and bandwidth. So this is a technical definition. In order to understand better, I'll just explain to you what exactly it is. Orthogonal frequency division multiplexing is a method of encoding digital data on multi-carrier frequencies. That is, instead of using just a single carrier frequency to carry the data, we'll be using multiple carrier frequencies. So how is it useful? OFDM has developed into a popular scheme for wideband digital communications used in applications such as digital television and audio broadcasting, DSL internet access, wireless networks, powerline networks, and 4G mobile communications. So that's pretty good applications, and that's the importance of OFDM in today's life. It is basically a digital multiple carrier modulation method in which a large number of closely spaced orthogonal subcarrier signals are used to carry data on several parallel data streams or channels. Each of the subcarrier is modulated with a conventional modulation scheme, such as quadrature amplitude modulation or phase shift keying, at a low symbol rate, maintaining total data rates similar to conventional single carrier modulation schemes within the same bandwidths. So what exactly will be the advantage of using OFDM over single carrier schemes? The one is its ability to cope with several channel conditions. For example, attenuation of high frequencies in a long copper wire, narrowband interference, and frequency selective fading due to multipath, without complex equalization filters. So you don't have to use complex equalization filters for considering the severe channel conditions, where in single carrier you'll have to consider all that. Channel equalization is simplified because OFDM may be viewed as using many slowly modulated narrowband signals rather than one rapidly modulated wideband signal. The low symbol rate makes the use of guard interval between the symbols affordable, making it possible to eliminate intersymbol interference. Now you might have studied about intersymbol interference, which is one of the major parameters considered and which basically limits the propagation of data. So OFDM considerably tries to overcome this limitation. I have a few exactly just I said about the advantages. If I just have to summarize it, it will be like high spectral efficiency as compared to other double sideband modulation schemes, spread spectrum. Then it can easily adapt to severe channel conditions without complex time domain equalization, robust against narrowband co-channel interference, robust against intersymbol interference, and fading caused by multipath propagation, efficient implementation using fast Fourier transform. Then it's low sensitivity to time synchronization errors, which is also one of the major parameters limiting in other modulation techniques. Then tuned sub-channel receiver filters are not required in OFDM. That is also a very one good advantage. It facilitates single frequency networks. So talking about all the advantages, we still have some limitations which we'll go through in the next forward slides, where we'll try to overcome them. One is the sensitivity to the Doppler shift. The Doppler shift you might have heard in simple, if I want to give an example, when a vehicle moves towards you, or for example an ambulance, the siren of the ambulance, or the intensity of the siren goes on increasing as it moves towards you, and it decreases, goes away from you. Basically that exactly is a Doppler shift in the frequency. Next is the sensitivity to frequency synchronization problems that OFDM will have to consider when using OFDM. The next is high peak to average power ratio, requiring linear transmitter circuitry which suffers from poor power efficiency. And the final is the loss of efficiency caused by adding a cyclic prefix or guard interval to avoid the intersymbol interference. So we like to talk about the general block diagram of how exactly OFDM is implemented. First, as you can see, the data comes in here. It is then converted into a parallel bit streams since we are using multiple subcarriers. It will be signal mapped, and then there will be a pilot sequence insertion. I'll go through details why exactly are we using this, and then there will be addition of a cyclic prefix with inverse fast Fourier transform, then digital to analog converter. It is up converted to the desired frequency and finally passed to the channel. At the receiver, an exactly opposite function takes place as that in the transmitter, as you can see. This is one diagram I found really useful if I have to summarize how exactly OFDM is calculated. As you can see, the multiple carrier frequency, these are the frequency response of the multiple subcarriers. So you might be thinking that, okay, there is some overlapping, so it definitely would corrupt data, right? So that's not really the case. If you consider it at the receiver evaluates each subcarrier at the point of its highest amplitude. So if I consider the second lobe, as you can see here, the value at this point for any of the other frequency is 0. As you can see, there is overlapping, but when I'm considering at the center, there is the value of that is 0. This is one of the major advantage of using OFDM. Next, we'd like to go through the channel estimation techniques. The radio channels in mobile radio systems are usually suffer from multipath fading, which are causing intersymbol interference in the received signal. To remove ISI from the signal, many kind of equalizers can be used. Channel estimation is based on known sequence of bits which is unique for a certain transmitter and which is repeated in every transmission bus. In channel estimation, what you exactly do is you pre-estimate the parameters to be considered at the receiver. So even before the data has arrived, you already know how to cope with the errors that might incur. Now, channel estimation, in our channel estimation, we have few techniques. It basically can be performed by either inserting pilot tones into all of the subcarriers of the OFDM symbols with a specific period, or inserting pilot tones into each OFDM symbol. The first one is the block type pilot channel estimation. As you can see in the first diagram, it has been developed under the assumption of a slow fading channel. Even with a decision feedback equalizer, this assumes that the channel transfer function is not changing very rapidly. So we assume that here. Estimation of the channel for this block type pilot arrangement can be based on the least square or the minimum mean square, that is LS or MMSE. The MMSE estimate has been shown to give 10 to 15 dB gain in signal to noise ratio for the same mean square error of channel estimation over LS estimate. In a low rank approximation is applied to linear MMSE by using the frequency correlation of channel to eliminate the major drawback of MMSE, which is complexity. Next one is the comb type. In the comb type pilot channel estimation, it introduces to satisfy the need for equalizing when the channel changes even in one OFDM block. The comb type pilot channel estimation consists of algorithms to estimate at the pilot frequencies and to interpolate the channel. The estimation of the channel at pilot frequencies for comb type based channel estimation can be based on the least square, minimum mean square error, or least mean square error, that is LMS. MMSE has shown to perform much better than LS. The complexity of MMSE is reduced by deriving an optimal low rank estimator with single value decomposition. The interpolation of the channel for comb type based channel estimation can depend on linear interpolation, second order interpolation, low pass interpolation, spline cubic interpolation, and time domain interpolation. If I go through every statement in this, it's a bit complicated to understand. So I'd just like to summarize in short, like a block, what exactly will be a block type channel estimation. The block type channel estimation is characterized by periodically transmitting pilot for every subcarrier. Here, to estimate the channel, a time domain interpolation is adopted along the time axis. As you can see, there is an interpolation of the time domain along the time axis. This block type estimation includes the least square estimator and the minimum mean square estimator. In the comb type of channel estimation, part of the subcarrier will be reserved as pilot for each channel. Each OFDM symbol will have pilot at subcarriers which are located periodically that are interpolated in frequency domain, thereby estimating channel parameters along the frequency axis. As you can see in the second diagram, the pilots have been included along the frequency axis, first had time axis. Lattice type channel estimation, which is a final type. In lattice type channel estimation, the pilots are included along both the time and the frequency axis. The interpolation takes place both in time and frequency domain. As you can see in the third diagram, the insertion of the pilot has been done both along the frequency as well as the time axis.